We've covered collinearity in 3 dimensions, so extrapolating out our 2D thoughts into a 3-dimensional scenario involving 3 points. What we're going to do in this video, I'm going to set you a couple of questions on this. I want you to read the questions, pause the video and have a crack at these. Here they are. First one is, I've given you 3 points, D, E and F. I want you to prove that they are collinear or not. Tell me what you know. Second one, if X, Y and Z are known to be collinear, there's a missing variable in Y, i.e. the X direction has a variable A. What is the value of this? And the last one, very similar to that, P, Q and R, they're all collinear, but this time if you look at R, I'm missing the Y and the Z direction variable. I want to know what those are. Pause the video and have a crack. So the first one, are the points D, E and F collinear? Well, to do that, we have to remember the properties of 3 points if they are collinear. We need 2 different vectors. So I've got the vectors DE, the vector EF, or the vector DF. So I've got 3 possibilities there. I need to pick any 2 of these. They need to be parallel to each other, i.e. a scalar multiple of each other. And they also have to share a common point. If they satisfy both of these conditions, all 3 points are collinear. So let's have a look at this one then. So I'm going to start by choosing the vector D to E. Now this is given by taking the position vector V minus the position vector D. Now remember, these are the vectors of the points here in relation to the origin. Quick and easy way to do it, turn these into column vectors. So it's 7, negative 6 and 9, take away 0, negative 3 and 5. 7 minus 0, well that's 7. Negative 6 take away negative 3, minus becomes a plus. Negative 6 plus 3 gives me negative 3. Then 9 minus 5 for the last one gives me 4. I can now look at any of the other 2 here. So let's look at E to F. This is given by doing F minus E. Again, our position vectors are the points in relation to the origin. That's 21, negative 12 and 17. Take away the 1 for E, 7, negative 6 and 9. Calculating these, 21 minus 7 gives me 14. Negative 12 minus 6, negative 12 plus 6 gives me negative 6. And 17 minus 9 gives me 8. So I've now got these 2 vectors. Can I somehow relate them to each other by making them a scalar multiple of one another? Well, this one here, if I take out a common factor of 2, I end up getting the vector 7, negative 3, 4, which is the same as this vector. From that, I can then write that E to F is given by 2 times the vector D to E. So what I've done here is I've taken the vectors and I've shown that one of them is a scalar multiple of each other. So they're both parallel. But another thing to look at is the fact that they share E. E is a common point between the 2 of them. So now not only do they have parallel vectors, multiples of each other, but they share a common point. So what this means is, since it satisfies both conditions, I can state this. Both vectors are parallel and E is a common point, therefore D, E and F in this case are collinear. So they've satisfied it, I've proven that they're collinear. This is the way that we have to do this and the steps we should follow. Second one, X, Y and Z are known to be collinear. What is the value of A? Well, the key thing here is they're known to be collinear. So if I take any pair of the vectors, they're scalar multiples of each other. I have to include this Y in it though. It's the one I want to find. I want to find out what the value of this A is. So if I take the vectors X to Y and I take the vector X to Z, what I'll find is they should be scalar multiples of each other and it will let me figure out what the value of A is. So if I look at the vector X to Y, that's the position vector of Y, take away the position vector of X. So in that case, it gives me A minus 1, negative 5 take away negative 2, and 9 minus 5. Simplify those down, and I get A minus 1 in the X direction, negative 5 minus 2, negative 5 plus 2 gives me negative 3, 9 minus 5 gives me 4. If I look at the X to Z one, I do the Z minus the X. So this one here, take away that one. So I've got 22 take away 1, negative 11 take away negative 2, and 17 minus 5. What that then lets me do is write it as 21, negative 11 minus minus 2, negative 11 plus 2 gives me negative 9, 17 take away 5 is 12. So I've now got to somehow relate these two vectors to each other. Well, this one here, what I can do is take a common factor of 3 and state that it's 3 brackets 7, negative 3, and 4. So what I can then say is, right, these two here are the same as here. So it's going to be a scalar multiple of this. I need to find a from it. So if that's the case, I can equate the x part here to the x part here. So I can then say a minus 1 must be 7. If a minus 1 is 7, that means that these are scalar multiples of each other, so it's going to work. So if a minus 1 equals 7, fairly straightforward equation for us to solve. A has to equal 8. So the a part of the y coordinate is 8. If I wanted to, I could write the y coordinate out as 8, comma negative 5, comma 9. So that's where the y is located for this to work. So there we go, we've found that variable. Let's imagine we expand it a little bit and say we've got these two variables to find. So we've got this scenario here. So the r has a y and a z that we don't know. And I've got all these here, so I need to find them. Well, the first thing we have to do is figure out all our vectors. So I want to figure out the p to q. That'll give me some numerical values. Then what I want to do is figure out the q to r and then the p to r. That'll let me get a few equations that I can then use to solve for these variables. So p to q, well, that's given by the q minus the p, which in this case is 1 take away negative 1, 2 take away 4, and 3 minus 8. So what that means is my vector pq, 1 minus minus 1, 1 plus 1 is 2, 2 minus 4 is negative 2, 3 minus 8 is negative 5. The vector q to r, given by the r minus the q. So there's my r there. So that's given by 5, take away 1, y minus 2, and z minus the 3. Simplify it all down, and I get 6, y minus 2, and z minus 3. Well, I can look at the two of these here and say, right, if these two are definitely parallel to each other and they share this common point of q, what I know is they must be scalar multiples of each other. So this one here must be some sort of scalar multiple of this. Well, if it's a 6 on the top, what I know then is that equals 3 of this vector. 3, negative 2, and negative 5. So it has to be equal to 3 of this vector. So what I then can say is that y minus 2 equals 3 times negative 2, and z minus 3 equals 3 times negative 5. Then I can solve these two equations and get y and z. So I then know that y minus 2 is equal to negative 6, y equals negative 4, and z minus 3 equals negative 15, z equals negative 12. So there you go, I've got my y and I've got my z. If I need to, I can state the coordinates of r based on that as being 5, negative 4, negative 12. That right there is where the r exists. So what I've done is I've used the fact that they're collinear, and then I've figured it out by calculating the vectors, setting them equal to each other and looking at the fact that they're scalar multiples of one another, and then worked it through from there.